All right, welcome back. Let's finish up these slides on functions and relations and then also start some new ones. So at the end of last time, we were talking about closure. That is when we had a relation that wasn't already reflexive or symmetric or transitive, but we wanted to make it that. We wanted to make the next bigger relation that is also reflexive, that is also symmetric, that is also transitive. We don't want to add too many extra relationships, just enough to get it to be reflexive or symmetric or transitive. Okay, so we talked about the rules, what you have to do, and now it's your turn. So try this. Please compute the transitive closure of the following relation R. And so here it is as a set of pairs. That's one way to write a relation, right? Which things are related to what. And so take this and compute the smallest relation that is all of these things plus just enough additions to make it a transitive relation. Okay, so you'll follow these rules right here. If you have x related to y and y related to z, you must add x related to z. And you keep doing that until there's nothing left to add under this rule. Okay, so give that a try, and then we'll do it together. So immediately, your answer, like if it's in terms of pairs again, right? Immediately your answer is going to be the original relation. So whatever the answer is, it's 3, 4, 2 still related to 7, 1 still related to 2, 4 is still related to 3, just like that. And then we're going to add some stuff. Okay? So that is the idea. And let's draw this out. That's the easiest way to compute the transitive closure, I would think, to just draw it all out. So it looks like the different elements that could be related are 1, 2, 3, 4, and 7. So let's try and draw that in a way that makes a little bit of sense. So here's 1, 2, 3, 4, and 7, let's say. Okay? And now let's draw arrows to represent the relationship. So 3 is related to 4, and remember that that is an arrow that way. Like 3 is on the left, 4 is on the right. It means 3 is related to 4 in that direction. Okay, there's a directionality to a relationship. And then 2 is related to 7, where 2 was on the left, 7 was on the right. Bam. 1's related to 2, and then 4 is related to 3. So we got this going on as well. All right, so that's the original relation. And now I want to add stuff to make it transitive. So whenever I have one thing related to something and then that something related to something else, I have a new arrow, right? I can go straight to the end of that. 1's related to 2, 2's related to 7. They match on the 2 in the middle. Now 1 is related to 7. That's what I have to add because it must be a transitive relation. This has to exist if the relation is transitive, right? So that needs to happen. And then also I have these guys that can wrap around. So 3 is related to 4, 4 is related to 3. That means 3 is related to itself now. If this were a transitive relation, that must be true. Same in the other direction. 4 is related to 3, 3 is related to 4. That means 4 must be related to 4 if this were a transitive relation, and we're trying to make it one. Okay? So that is, I think, everything that needs to be added. So 1 must be related to 7, 3 must be related to 3, and 4 must be related to 4. And this addition makes it a transitive relation. Okay? So this whole thing is the transitive closure of R. It is the smallest relation containing all of these that is also transitive. Okay? So hopefully that makes enough sense. Please yell at me if it does not. But I want to move on now to something very important called an equivalence relation. Okay? We say that a relation R, if it's so cool to be reflexive, symmetric, and transitive at the same time, we call that an equivalence relation. Okay? And there's a very good reason why we say this. Why does this mean that the relationship is an equivalence? Like two elements, if they're related, are equivalent to each other. Well, there's a very, very important relation that is reflexive, symmetric, and transitive. It is equality, right? 2 is related to 2 under equality, right? That makes sense. It is a reflexive relation. It's also a symmetric relation. If x is equal to 5, then 5 is equal to x, right? And then it's also transitive. So if x is equal to y and y is equal to z, then obviously x must be equal to z too, right? Everything that is equivalent is the same. Everything that's equal is the same. And so this is why we call it an equivalence relation. If you have a relation that has all these three properties, it's essentially mimicking equality, okay? And so each of these elements, like x and 5, those are the same thing. Those are equivalent things. X and y and z, those are all the same thing, okay? That's why we call it equivalence relation. And so instead of saying A or B, when A is related to B under an equivalence relation, We say A squiggle B in the book, at least. They say that, and so we'll use it too. That just means it's more powerful than saying A is related to B. No, A is equivalent to B. Those are essentially the same thing. A is essentially the same as B at that point. Okay? And so here are some examples of equivalence relations. Let's number these like 1, 2, 3, 4, 5, and 6, and pretend that these are all separate relations, by the way. I guess I'll draw this. That's fine. These are all separate relations, but they're all equivalence relations, right? All the properties are upheld like this. These are all reflexive, symmetric. You can go from 1 to 3, 1 and backwards, 1 to 2, 2 to 1, and 1 to 2, 2 to 3. Then you also have 1 to 3. It's transitive as well. Like, you can get from any of these to anybody else. They are the same. They share all the same properties, right? That's essentially how. You can move around to anybody here. All of those elements are essentially the same. There's a way to get from one to the other. They're all related to each other. They all have the same properties. And so for all intents and purposes, you could say 1, 2, or 3 are equivalent. There's a way to get from each of them to the rest. Okay, same for this one. These are equivalent because it's symmetric, transitive, and reflexive. The reflexivity, symmetricity, transitivity also gives you reflexivity again. It works out. And if this is just a single relation with a single element, well, it is obviously reflexive, but it's also just vacuously symmetric and transitive because there's nobody else. Okay, so these are all equivalence relations. Like 4 is equivalent to 5. It shares all the same properties. There's a way to get to it. That's what it means, okay? And because they're all the same, like x and 5 are the same, x, y, and z are the same, we want to be able to talk about that idea. Like, you could have used 1, 2, or 3 and equivalently, right? You could have replaced 1 for 3 in your argument, and because they're equivalent things, they didn't really make any difference, okay? So to talk about all the elements that are equivalent to each other, we use this concept called equivalence classes, okay? So if you have some element and you put some brackets around it, some element in your relations domain, if you put brackets around it, that's called the equivalence class of A, okay? And that is defined to be all the other elements, all the x's in A. It doesn't have to be other elements because it's reflexive. A is there too. All the elements in the domain such that A is equivalent to x, okay? A is related to x under that relation. And so this set, it's all the things that are equivalent to A. It's called an equivalence class. Okay, so for example, like what is the equivalence class of the element 1? Well, what are all the things that are equivalent to it under the equivalence relation? It's, well, 1 because it's reflexive, and then 2 and 3. Yep, they're all linked to each other. And notice that this is equal to the equivalence class of 2, which is equal to the equivalence class of 3. What are all the things equivalent to 2? Well, it's all these again. Same as for 1, same as for 3. So that's kind of all interchangeable because they're equivalent elements. Yeah? I hope that makes enough sense. Same for this one, like what's the equivalence class of 4? Well, it's whatever the equivalence class of 5 is because those are equivalent elements, and it's just all the things that are related. 4 and 5. Yeah? And then same for here. What's the equivalence class of 6? Well, it's just 6. There's nothing else it's linked to. That's the one element in the relation. Okay? So this is just an easy way to talk about all the things that are equivalent to other things instead of writing out a potentially very large set. Okay? So that's what it means to be an equivalence relation, and it's because of equality that we call it that. Like the essence of equality is being reflexive, symmetric, and transitive. All right. So we can talk about some interesting things that happen under an equivalence relation. Okay? When we have an equivalence relation, we can talk about, okay, what are all the elements that are equivalent? So now let's pretend that really this is the same relation. These didn't have to be separate, okay? Let's pretend this now. So if these are different pieces of the same relation, it looks like only some things are equivalent to other things, and that's fine. That's totally okay. It doesn't have to be the case that everything is equivalent to everything else. Maybe some things are equivalent to each other and other things are equivalent to other things. That's totally fine. So if this is one big relationship, you can see how it kind of splits itself into all things that are equivalent to each other. Okay? Like all these are equivalent, it's just one big chunk. All these are equivalent, another big chunk. All these are equivalent, another big chunk. And it kind of sections off the domain. Boop, boop, boop. So now dotted lines. Okay, so this is one big relation now. And it partitions, is what we say. It partitions all the elements of that set under the relation, all right, under the equivalence relation. So a partition of a set is a set of non-empty subsets that are pairwise disjoint, so they don't share any elements, and whose union is the whole thing. Okay? Or that pairwise disjoint just means they don't share any elements, the sets don't overlap. And equivalence relations actually partition a set. So for every partitioning of a set that we learned about before, there is secretly an equivalence relation for that partition, okay? For that partitioning scheme. There's a way to make a relation that gets all of these things to be in its own little chunk, all these things in its own little chunk, things like that, okay? So partitions are nice. They link us to equivalence classes. Those concepts are intertwined. So yeah, let's talk about that. So this is essentially creating a bunch of different pieces of the same set. Like all these things are equivalent. This is a partition. Like, okay, this is all these three things together make up a partition of the set. Each thing that is equivalent, they section off the rest of the domain. Okay, so I think that's all I want to say there. The last thing is, if you add an arrow, if you link one of these sets to the other, because this is an equivalence relation, you know you must have this, you know you must have transitivity, and so you just merged by adding one arrow, and because the rest of it's all an equivalence relation, you just merged these two equivalence classes. You see that? Isn't that interesting? So yeah, there's a lot to say about this, but it's best shown in diagram form. If you have an equivalence class, or an equivalence relation, all the equivalence classes section off the set into partitions. All right, so that's a bunch of terms. Now, let me give you something to try yourself. So here is a relation. Let's define x to be related to y if x minus y is equal to 3m for some integer m. So x minus y is a multiple of 3. Yeah? X is related to y if that is true, where x and y are integers. And see if you can figure out if this is an equivalence relation. Is it reflexive? Is it transitive? Is it symmetric? Because that's what it needs in order to be an equivalence relation. So see if you can figure that out, and then we'll come back and try it together. So we better check each of these three things. Is it a reflexive relation? Is it a symmetric relation? Is it a transitive relation? Where like the difficulty gets harder as you go down the list. So that's why we're going to do it in that order. So let's just think about like what things are in these equivalence classes, or not assuming that it's an equivalence relation. Like what are some examples of things that are related to each other under this relation? So like, I don't know, x minus y is equal to some multiple of 3. So it looks like, I don't know, 6 and 3 are related under R, right? Because 6 minus 3 is equal to 3. So where m is 1, that works. Same with like 9 and 6, that works. Because 9 minus 6 is again 3, where m is 1, that's still a multiple of 3. Things like that. So those are some examples, and you can write as many as you want to get a feel for it. And now let's try and check reflexivity. So what does it mean to be reflexive? It looks like where m is 0, kind of. Maybe that would help with some more examples. Like if m is 0, what do we get? If m is 1, what are all the things that are related? That might be a better place to go next. So if m is 0, that's like saying that means x minus y is equal to 0. So that's a bunch of equivalent elements. So like 1 and 1, 2 and 2. Interesting. 3 and 3. Interesting. That might help us for reflexivity. What's true when m is 1? So that's like 6 and 3, 9 and 6, 4 and 1. 4 minus 1 is 3. So that is like that if m is 1. And then if m is 2, that means what minus what is equal to 6. So we have like 6 and 0, 7 and 1, 8 and 2, Those are all related under this idea. Okay, so this is the relation. Now I think we have more stuff that we can use to figure out if it's reflexive, symmetric, or transitive. Okay, so if it's reflexive, that means that every element must be related to itself. Is that true? Is it true that x is related to x? Well, if it is, that means x is related to y. If this is all true, I chopped off a part of the x, sorry. So, all right, just unpacking this, it's reflexive if for every element x minus x, we're trying to relate it to itself, right, is equal to 3m for some m. So is 0 equal to 3m for some m? Yeah, m can be 0. Do you see that? 0 equals 3 times 0. That's totally fine. And so it looks like this is indeed a reflexive relation. Isn't that nice? I hope that makes sense. Let's also talk about symmetric. So is this a symmetric relation? That means if I know that x is related to y, is it true that y is also related to x? So if I know that x is related to y, that means x minus y is equal to 3m for some m. Is it also true that y minus x is equal to 3m prime for some other m? Is that true? And I do believe it is, because if you use these two ideas, x minus y, how do you relate that to y minus x? I could just multiply by 1 on each side of this equation, right? Or by -1, by -1. If I multiplied that, then I get y minus x is equal to negative 3m. Okay? So it looks like my m prime is just negative m, solving for these. You see that? Negative original m. So there is another integer, namely negative m, such that this is true, which means that y is then related to x on the other side. Okay, so it's also symmetric. Do we see how we're proving that? And then finally, is this a transitive relation? Let's see if we can figure that out. So if I know that x is related to y, that means that x minus y equals 3m for some m. And also I know that y is related to z, so y minus z is equal to 3m prime, or let's say m1 and m2 here. If I know these three things, is it also true that x is related to z? So I need some way of relating x and z, so x minus z is equal to 3 times something, some m3. Is that true? Question mark. Okay. So how can I use these to maybe get this? If I can, if there is always a way, then it is a transitive relation. Okay? So let's see if we can figure this out. So, if I know this and then I know this, how can I get the third thing? I guess you can solve for one in terms of the other. Let's maybe, I think I can add both of these equations, actually. Let's add both of these sides of the equations to each other. So x minus y plus y minus z, the y's cancel. That's nice. So x minus y plus y minus z equal to 3m1 plus 3m2. And then the y's cancel, and then I'm left with x minus z equal to 3m1 plus 3m2. Let's get the 3's out like this, m1 plus m2. Do you see that? I just found another integer multiple of 3 equal to x minus z. And that's all I needed for x to be related to y. So it looks like it's also transitive. Did you follow that? There's a lot going on there, a lot of math necessary, but we did it. We just proved that this was an equivalence relation. And that means everything that's related to the other thing is equivalent. And secretly, what this is trying to calculate, what are the equivalence classes of this? It's every different output when you perform mod 3, okay? Those are all the equivalence classes. So mod 3 equivalence relation. That's really what's happening here, because 0 is related to 3, 3 is related to 6, it's also transitive, symmetric, 9, 12. These are all the elements that are equivalent to 0 mod 3. That's your first equivalence relation, or your first equivalence class. Then you have 1 and 4 and 7, all the things that are equivalent to 1 mod 3. And then you have like your 2, your 5, your 8, blah, blah, blah. That's your third and only equivalence class. Okay? So there's 3 equivalence classes total because there's 3 different answers you could get by taking mod 3. Isn't that interesting? So yeah, this is really an equivalence relation, and we proved it with math. So that is a good example to study, see if you can recreate that proof. And now let's get into relations on more than one element. So it's totally fine, not a problem, to have relations on more than 2 things at once. I can say that, like, I have a relationship on 3 different things at once, a relationship on 4 things at once. It's not a big deal, okay? So let's make this happen, okay? So if you have a relation and you have a bunch of sets to relate at once, well, a relationship on all these sets at once is just a subset of this Cartesian product. It's just a bunch of pairs of all these elements in order. That's all. It's called an n-area relation when there's n things that you're relating at once. That is not a problem. So just like you can relate x and y, z is related to w, you can also have a relationship between a bunch of things at once, like x and y and z and w. Those are all related to each other under a certain relationship. All right? P and Q and R and S, those are all forming a relationship with one another. Okay? And that's all it is. That is an n-area relation. It's interesting to think about. There are plenty of things that fall under the category of a relation that is bigger than 2 things at once. Okay? In fact, a very important thing in computer science, an important relationship in computer science, is input and output of a program or maybe a single function, because a lot of the time your input is more than just one parameter, right? A bunch of inputs make a single output, and you could think of it as a bunch of all of those inputs are related to the output. Okay? So, for example, the append function in Racket, or you could define the equivalent thing in C++. It takes 2 lists, right? And then it gives back a bigger list with those 2 smaller lists concatenated together. That's what append does. You can define in a relation, a 3-area relation, on lists that covers what append is really doing to its input lists. Okay? So you could define this relation, call it append. It's all of these triples of elements, x, y, and z, where x, y, and z are lists, and appending x to y gives you z. You see how there's a natural relationship between these first 2 elements and this last one? That's a 3-area relation. Okay? Or trinary relation, however you want to pronounce it. So here are some examples of things that are in that relation. Let's go back to blue. So for example, the list 1, 2, and the list 2, 3, if those are the first 2 elements, they are related to the list 1, 2, 2, 3. Okay? So that's an element under this append relation, because this appended with this is equal to that. There, you can relate anything you want. Input and output is a good idea, though. So you can also relate under this relation the list with just 1 in it and the list with just 42 in it to the list that is returned by appending these. So that gives us 1 and 42. So those are related under this append relationship. Okay? So that is a way to talk about what it means for functions to do. You can define a relation that kind of says exactly what is supposed to happen when you run a function with certain input, and this is the output that you must get back. Okay? And this will help us as we eventually want to prove that our programs are correct. Okay? We can use an n-area relation on the inputs, taking the input to the output. Okay? That's quite nice. And then finally, let's give us some examples. Let's have some practice with these n-area relations. Here's a 4-area relation, okay? And I want you to express it as a set of tuples, a set of n tuples, right? Where this is a n-area relation. So there's 4 things related, so it's 4 tuples. All of your elements are going to be of size 4. So here is the relation. A, B, C, and D are related to each other if they're all positive integers and their sum is 6. Okay? So see if you can express this relation as just a set of concrete elements. Okay? What does this relation mean? All right? You can totally write a program to find this, but we'll do it by hand right now. All right? So for example, let's think of a nice ordering for this. 1, 1, 1 would force the last element to be 3, right? Because it needs to add up to 6. So this is one element of this relation R. You see that? 1 and 1 and 1 and 3 are all related under this relation. Okay? In that order. That is a fine relationship because they add up to be 6 and they're all positive integers. Yeah? What's the next one? So 1, 1, let's make this a 2 because I can't make this a 4, and that will force this last one to be 3, 4, it'll be a 2. Yeah. So these are more elements that add up to 6, and that is a fine relation. Like here's 4 things that add up to 6. That relates all these elements. Same with this one, like 1, 1, let's make that second one a 3 now, and that forces this to be a 1. Okay? And you could follow this pattern. It goes 1, 2, 1, 2, 1, 2, 2, 1. I thought of this ahead of time. I'm not this fast on my feet. 1, 3, 1, 1. But you can see there's a kind of order. It's like, okay, this is smaller than this, kind of. I'm trying to add 1 to the next possible element that I can add 1 to. Like I can't do it anymore to this one. That'll make it too big, so now I have to look at this one. Make it incremented. Now it's a 2. Yeah, that's the idea. 2, 1, 1, 2. These are all the elements that are related to each other under this relationship. 2, 1, 2, 1. They all add up to 6. 2, 2, 1, 1, and 3, 1, 1, 1. And if you're not sure about what elements are fit under this relation, you can totally write a program to do this. Just have a four-way nested for loop, right? Quadruply nested for loop that tries all the possibilities and outputs whenever it finds that this is true. Okay? That's one way to solve for this. So that is a four-array relation, and we just wrote it out in set form. Okay? So that is the end of our functions and relations slides. Yay, we did it. So let's check the time and see how much more we can do. I want to get started on the next set of slides now, talking about real computer sciencey stuff, algorithm analysis. Let's go further than we went in CSCI 41 now. Okay, are you ready? So let's talk about that a little bit, and there's a lot to cover. So let's just talk about algorithms in a nutshell right now. What in the world is an algorithm? Well, it's just a recipe, right? It's a sequence of steps to solve some problem that you're given. All that it really is a recipe. Like, all right, the recipe for pancakes is, okay, take inputs, flour and milk, eggs, baking soda, whatever, and that gives you as output pancakes, right? That is an algorithm. It's just a recipe. It's how do you take your input to your output, all right? And our goal for this class is to be able to formally reason about programs. This is a computer science class after all, but we have to learn a lot of math to do it. That means we need to be able to talk about what every statement when we write a program, what it really does, okay? We're going to talk about, just at a higher level than a normal language like C++, we're going to talk about pseudocode in this lecture, but keeps doing that. But this could totally be translated to C++ very easily. Okay, so we want to talk about like every statement, every line that we could write in pseudocode. What does that mean, really? What's it doing? And that is how we're going to represent programs. If we don't allow functions, let's just say that we allow the body of a function, and that's an algorithm or something, then if we don't allow functions, we don't have to model the stack mathematically, and we can just say that the state of the program could be represented by just all the values of the local variables, any variable that's alive at the time, okay? And that's how we can represent the current state of a program. It's just what are all the places, what are all the variables and what are the values that they hold. Yeah? So that's not too bad. So, for example, here is a sample little algorithm like x gets to be 4. I think your book uses the colon equals. That is an assignment statement. It's meant to be imagined as an arrow, right? Going to the left. And then x assigned to be x plus 1. If we take this viewpoint, then like this is line 1, this is line 2, and here's an algorithm, we can talk about the state of a program as it progresses. So for example, like right here, the state of the program is all the values of the variables. Like x right now holds 4. And then right here, after this second line completes, given this previous state, the new state of the program is x holds 5, because there's only one variable to talk about right now. Okay? So the state of a program, this is a key fact, we can just talk about the values of the variables, all the ones that are alive. That's what it means to be, to know what's happening right now as our program is progressing. Okay? And yeah, that is assignment in a nutshell. An assignment statement, it makes a new state by changing one variable from the previous state, right? It's only ever writing to a single variable at once. It may be using other variables, but that's what it's doing. It's writing things. So there was an old state, maybe like old state, where, I don't know, x was 42 and y was 7. And then after this line completes, x has been changed, right? We're writing to x. And now there's some concept of a new state that exists right here. New state. Where, well, given the values of the previous variables, x has become whatever y was. Y was 7. So x is now 7, and y is still 7. See that? Only one variable changed. It was x. So that is an assignment statement. That's how it changes the state of a program. And if we talk about mathematically how these states change for every different kind of pseudocode statement, we can formally reason about programs mathematically. Isn't that cool? That's what we want to do. All right? So now let's keep going. Let's talk about how to execute an if statement or an if-else statement. How does that work? And this is, of course, everything that we know and love already. It just is in pseudocode, right? This is how your book is going to write it. So yeah, what does an if statement really do as it executes? Let's talk about this so that we can represent it mathematically. So an if statement, what does it do? It executes code if a condition is true. Right? So if this is true, then do all these. Otherwise, don't do them. Yeah? Let's represent that mathematically. Let's write a little tree for how it's going to execute. If-else statements as well, they're going to execute the true branch if this condition is true. Going to do all these. Otherwise, if it's false, then we're going to execute the false branch, the else case. Okay? Only one of these two options is ever going to be completed, and we have to be very careful about how we model that. So the very first thing that happens is we test our condition, given the current state of the program. And then if it's true, we're going to execute the body of the if, right? Execute body of the if case, the if statement. Right? And then if it's false, we're going to execute the body of the else case, if we're talking about this one, for example. And so we've made it very clear that you can't run both of these bodies, right? One or the other. Execute body of else case, if there is one. And so this now covers this one too. And then, once either of those has completed, we go on to the rest of the program, right? That's what it means for an if statement to execute. And if we could represent this mathematically, it becomes a very powerful idea. We can reason formally about our programs. Let's keep going. Let's talk about loops. What does it mean for a loop to execute? Right? A while loop, for example, it repeatedly is going to execute its body as long as a condition is true. We have to spell this out when we're talking about it mathematically and formally, right? So it's going to keep on doing these as long as the condition is true. So it's going to try the condition. Then if it's true, it's going to execute the body. and then it's going to go back and check the condition because maybe it's still true and it needs to complete the body again and again and again in a looping fashion, right? So that is where the loop happens. All the arrows come together like that and make a loop. And then if the condition is ever false, right, we go on and we do the rest of the code. Rest of code. Then the while loop is completed, right? We do the rest. So that is essentially how a while loop executes, right? To talk about it even more formally, we know something very special, right? About what happens when we ever get here, right? We know if we're ever done with the loop, then that means the condition has become false, right? The condition must be false. So if a loop ever stops, if it's not an infinite loop, that means its condition must have become false. We know right here, in addition to all the other things that we know that not condition is true, right? Because otherwise it would have continued the loop. Hey, isn't that interesting? So we have some extra information about what happens at the end of a loop if it is not infinite, if it continues. All right? And you can look at your book. I mean, I'm forcing you to read the book. It's going to talk about for loops and how those execute formally, but they are essentially the same as while loops, so I'll just skip them here. Okay? That is that. So with that in mind, I would like you to use this style of pseudocode. Just get some practice with it. While looks like that, if looks like that. Just try to write English rather than C++, because that's what you're used to, right? Try and write an algorithm that does this, okay? Write an algorithm that does this for this representation of the input, and here's what you should be outputting, okay? Here's what I want you to do. So you're going to take a sequence of numbers, A1 through AN. So this is higher level than C++. Maybe you can imagine this to be a vector, to be an array, but you're getting a sequence of elements that are accessible, A1 through AN. It doesn't even start at 0, which is crazy, where n is greater than or equal to 1. So you're forced to think about this in a different way. And then you also have the length of the sequence. So you're given how many elements you have in this sequence, whatever it's really saved as, a vector, an array, whatever, a linked list. So that's your input, and then your output is, I want you to output true or false, okay? True if you can find two different numbers in the sequence who sum to be 0, and false otherwise. Can you solve this problem? So you're given a bunch of numbers and their length, and then you have to go through them somehow and see if you can find two different numbers in that sequence who sum together to be 0, and if you can't find any of those numbers, you output false, okay? There's a bunch of different answers. There is a very tricky way to make this a linear time algorithm, which is crazy, but I'll show you the n-squared version on the next slide as you think about it. So take some time, try this out, and then we'll come back and talk about it. I'll check my time in the meantime. So, yeah, I think the standard way of doing this would be a doubly nested for loop, right? So you do something like for I equals 0 to, oh sorry, we're starting at 1 because the sequence starts at 1. A1 is the first element. So for I equal 1 to n, and then for, and this is the body, right? For j equal 1 to n, then you try them all, right? If ai plus aj is equal to 0, and I is not the same as j, because it needs to be two separate elements, right? If that's true, then return true. Yeah. Otherwise, return false. If we got through every single pair of elements, way down here, we can return false. So that is very obviously n squared. Let me do you one better. Let me duplicate this slide, and let me show you how you can cut off some of these elements so that you don't have to check this. Here's a slightly better way of doing it. So let's introduce some kind of ordering. So let's say that n can go between 1 and n minus 1, and j must then go between I plus 1, so it's never going to be I, to n. So now these will never overlap. Yay. And these will now return true under the same circumstances and false otherwise if you didn't find anything. So we cut off a lot of the space, a lot of duplicated effort, by forcing I to always be smaller than j. Okay? And that is still going to cover all the possibilities, just in a very interesting way. Okay? So for example, before we were doing this, we were testing A1 and A3. Hey, is that 0? Maybe I should write this on the previous slide. Before, we were testing like A1 plus A3. Hey, is that equal to 0? Then we were also testing A3 plus A1. Hey, is that also equal to 0? That is duplicated work, right? Where I is 1, j is 3, and then here I is 3, j is 1. That's duplicated work. We only ever want to do one of these, and so let's do the first one only and skip this one by forcing I to always be less than j. Okay? And so that's what I'm doing here. I is always going to be less than j, and you're still going to cover all the possibilities. And this is still O of n squared. It's just better. The constant out in front of the n squared is much better for this one. The reason why is this is still essentially n times. And for most of these loops, like this is for the first iteration going to go between 2 and n, that's essentially n times as well. And so those multiply together to give us O of n squared. There's definitely a more fancy way to analyze this, but we won't go there right now. Okay, so this is an n squared algorithm. Talk to me in office hours if you'd like to hear the linear time solution. It involves, one way to do it involves a hash table, which is cool. So we can talk about that offline if you would like. But that is where I want to get it. So we just talked about what it means to execute statements. We're trying to mathematically specify how our programs are going to work. Let me check our time, see how we're doing. Yeah, let's try to do maybe this slide, and then we'll talk about big O again next time. So we're trying to go a bit further, because in CSCI 41 we learned about like all of our notations, how to analyze algorithms. We're going to do that a bit more formally now that we have a lot of mathematical machinery behind us that we know about. So that's where we're going, but I think this will be the last slide for this lecture at least. Okay? So let's talk about the asymptotic growth of functions, because that is what O of n is doing, like O of whatever, big O notation, big theta notation, big omega notation, if you've heard of all of those. Those are representing the asymptotic growth of how a function is getting bigger. So remember, like asymptotes from math class, it's something like, okay, looks something like this, right? This is an asymptote. It's saying this is kind of bounding how big a function's value is ever going to get. So that's essentially what we're doing when we use big O. Like we're giving a mathematical specification of how big this thing is ever going to get, how big the number of steps this program is going to take as the input gets bigger. Okay? So yeah, the asymptotic growth of a function is just how fast the output of that function, so apply it to something, how fast that grows as the input grows. Okay? So how fast the output grows as the input grows. That's the key. That's what asymptotic growth means. And we're looking for that bound, that dotted line essentially. We want to know, like we want a very simple way to talk about how big things are getting, how much work we're doing as our input grows. Okay? And we like to simplify. So we don't really care like exactly how fast the function's growing. Like we don't care about maybe there's some plus n terms, some constant terms. We just care about the n squared as programmers. Okay? That's like an equivalence class of programs, things that are n squared, O of n squared. So yeah, there's a bunch of different ways to write the same function. There's an infinite number of them. And we don't really care about the specifics. Okay? We just want to lump similar functions together into equivalence classes. Equivalence classes, like, they're all linear, they're all quadratic, they're all exponential, right? And talk about some of those as being good and some of those as being horrible, and we don't ever want to use them, right? So, yeah, we have used big O, which I'm certain that you know about from 41, and then potentially you have also learned about big omega and big theta as well. Okay, and those are different ways of talking about how a function grows, how to bound it. And so these are pronounced as big O, big omega, and big theta. And yeah, this is where we're going. So like we're going to mathematically specify what all of these really mean, assuming you learned about them before from a very like intuitive perspective, not a very mathematical perspective, because that's how we tend to teach it in CSCI 41. But the idea is we can use other functions to bound other functions. So for example, like I want a function that always bounds this one. Well, I want a very simple one, a much simpler version than this. Here's a function that bounds it. It's always above it, something like that. And maybe this one's so much easier to write. Like there's the equation for this one's much simpler than this function. That's essentially what we're doing. That's what we're trying to get at. Okay? We're trying to write a simpler function that can help us, that's always bigger than another, that can bound another function, and that lets us categorize it. Okay? How fast is it for a certain input? All right? And so next time we're going to get into big O, big omega, and big theta and talk about what this all really means. So I will see you in the next lecture.